In this video, we will talk about what improper integrals are and how to recognize them. So recall that a definite integral over some interval from a to b of a function f of x is defined when our interval from a to b is a finite interval. So when we first defined definite integrals, it was sort of implicitly assumed that our interval from a to b was a finite interval. Oops, sorry, no plural there, just interval. And the other condition that we needed for it to be defined was that f, our function, needed to be continuous on that interval from a to b, that closed interval. It turns out we can relax that second condition a little bit. So this is still true, it's still defined if f has finitely many what are called jump discontinuities. All right. So let's draw a picture of what that would look like. Okay, so let's scroll it down to give ourselves some room here. All right, now I'm going to draw a picture. So I'm going to draw some axes. And let's say that this is 2, this is 4, and then somewhere further down, this is 9. And my function looks something like, it starts at 2, then it goes up for a while until I reach 4, and there's an open circle there. And then I have another open circle at 4. So it sort of jumps down from where it was on one side, approaching 4, to where it is on the other side, approaching 4. So this is called a jump discontinuity. Okay, and then it decreases, crosses the x-axis somewhere, and then it keeps going down. And then let's say I have a closed circle over here at 9. So for example, so e.g., let's say I wanted to evaluate the integral from 2 to 9 of this function, f of x dx. So what I could do is I could split this up into areas, positive and negative ones. So first, I'll put a boundary at 2. I'll put a boundary at 9, because those are the endpoints of my interval. And where this jump discontinuity happens, I'm also going to draw a dashed line. All right, and what that does is it divides this region into subregions that I can describe. Okay, so this first region from 2 to 4, I'm going to call this A1. And let's just suppose that A1 is 7 for the sake of example. And this next region, from 4 up until where the curve hits the x-axis, I'm going to call that one A2. And let's say that A2 is 3. And this final region, I'm going to call A3, and let's say that that area of A3 is 5. So using this notation, my integral here is equal to the first area plus the second area minus the third area, because A3 is below the x-axis, so it gets counted as a negative area. All right, so now when we plug in our numbers, A1 is 7 plus A2 is 3, and then minus A3, so minus 5. So evaluating this, we'll get 5. So it's possible for us to handle these definite integrals when we have jump discontinuities like this. Essentially, we would split up our integral at those places where the jump discontinuities occurred, and then handle each one of those smaller intervals in the same way that we typically handle a definite integral. All right, so our goal in this section is to evaluate a bigger class of integrals than just the ones that we've been able to do up until this point. So we are now going to try to evaluate integrals where one of two things happen. So the first possibility is, what if the interval from a to b is no longer finite? What if it is infinite? So if it was infinite, that would mean that either a, the smaller of these endpoints, is negative infinity, and or b, the larger of the two endpoints is positive infinity. So let me draw a picture of one such situation. So let's say I have my axes, and let's say this is A, and my curve looks something like this. So if I had the definite integral from where A is, extending all the way to positive infinity at the right end, the definite integral would correspond to this area. This area of this infinitely long region, because this is an infinitely long interval. Okay, so sometimes we're going to be interested in evaluating integrals like that and finding, well, how big is this area? It turns out sometimes areas like this, even though this is an infinitely long region, end up having finite areas, which is really bizarre. And we'll see an example of that in the next video. Okay, the other type of integral we will handle is when f, our function, has an infinite discontinuity on our interval from A to B. So let's draw an example of that. Okay, so if I draw some axes, let's say this is where A is, and this is where B is, and my graph does something like the following. Let's say it gets infinitely large somewhere in the middle of the interval, because there's a vertical asymptote. And then maybe on this side, it's doing something else. Okay, so if I wanted to evaluate it on this interval from A to B, let me draw dashed lines where A is and where B is. We would be finding the area in this picture of this part, and then we also have to add it to the area that occurs on the other side of that vertical asymptote all the way until B. So even though that this region gets infinitely high because my function gets infinitely large, there are situations where this area is finite, and we will see examples like that. There are also plenty of examples where integrals of both of these types that correspond to areas of regions like this give us an infinite area, so that can happen as well. So in terms of our goals for this section, we have now finished our first goal. We've defined what improper integrals are and talked about what will they look like. Either they'll have one of the limits of integration be positive or negative infinity, sometimes both of them, we'll get a negative infinity to positive infinity, or the second scenario is where our function becomes infinite somewhere on the interval because of a vertical asymptote. In the next video, we will define type 1 improper integrals a little bit more formally and do a few examples.